Hello, in this video we're going to look at some graphical representations of everything that's going on in SHM, in simple harmonic motion. So position, velocity, acceleration and various stuff to do with energy. That will cover most of what we're going to look at here. Right, so, oh, and forces, that'll be another one. Let's note down our equations again, because these are all the things we're going to be drawing out. So we've got, just get on the right slide, we've got S equals A. Which one should we go? Let's go cos this time. I mean, as I've been saying all the way through, it doesn't matter if you do cos or sine on this. It's still the same function. It's just an offset in the x-axis when we're thinking of transformations of graphs. Then we've got minus A omega sine omega t plus phi for our velocity, and our acceleration would then be minus A omega squared, back to cos again, omega t plus phi. Okie dokie. So these ones are quite easy to draw out. We're just drawing some kind of sine function or cos function. So we're drawing if we're starting here, we're doing t and we're doing our displacement. Now it's going to depend, where we start is going to depend on phi, because remember this is our phase shift that we're starting with. It's sort of deciding where t is 0 essentially by putting that there. So although we've got cos sitting here, we've gone cos sine cos on this rather than sine cos sine as we're moving from displacement to velocity to acceleration. It doesn't really matter because this phase shift can take care of any difference between cos and sine. So we can pretty much draw in whatever we want here, providing it's in our usual sine wave style. A little bit wonky, but you know what a sine wave looks like. So our phase shift phi here is going to determine exactly where we are in the cycle. Our omega here, that is going to determine the frequency. This is our angular velocity that we've got in the associated circular motion, and that is going to determine how quickly we're completing each one of these oscillations. So omega is telling us how tightly packed all of this is. So if we increase omega, and this is thinking of your transformations of graphs, if we increase omega, we still have the same amplitude, but we'll be going through oscillations a lot quicker. So that's for a higher omega. Excuse me. A here is the amplitude. So that's going to be going between A and minus A on there. So we can see how all these bits fit in. This phase shift is shifting things to the left and to the right. The omega is squashing things in the x direction, and A is stretching things in the y direction. I mean, I have left out, we could have had this S0 bit here. We could have been shifting up and down as well in the y direction. But yeah, I've just set the 0 displacement to be the equilibrium point. But if that wasn't we weren't saying 0 was the equilibrium point, then we can have this S0 and just shift all of the graph up and down as well. And the other graphs are pretty similar, really, because we're doing exactly the same things going on here. For the velocity, it's going to look much the same, except we're now drawing a sine graph rather than a cos graph, because we're taking the gradient of all of this. So we've got an additional shift in phase, that's our actual phase shift, the phi. But just comparing the graph of displacement to velocity, we've got another pi by 2 phase shift. So yeah, we'll be shifting everything along by pi by 2. So we're going to start in a different place on this. We're starting positive and we're quickly going negative. We'll be comparing it to the original graph. It's going to have the same frequency to it because we've got the same omega, which is determining how squashed we are in the x direction, and now we're varying between A omega and minus A omega on our maximum and minimum speeds. So yeah, these are quite straightforward. And then for acceleration, we've got our original graph, but flipped upside down and multiplied by omega squared. Otherwise, we haven't really got any difference. So we're going to be starting on the other side and doing all of that. And then we're going between minus a omega squared and plus a omega squared as our top and bottom values of acceleration versus time. So these are all quite easy to draw out, and it fits in really nicely with our transformation of graphs that we've done in maths. Okay, let's start looking then at energy, and something which is going to be useful with energy, which isn't immediately obvious when you're looking at these equations. But what would happen if we did omega squared s squared plus v squared? What's going to happen if we actually work all of this out? Well, omega squared s squared is going to be a squared omega squared cos squared, all of the stuff in the brackets, so omega t plus phi, and then v squared is a squared omega squared sine squared omega t plus phi. So we got the same a squared omega squared, and then we got a cos squared plus sine squared. So they're just going to cancel out from our trig identity of sine squared plus cos squared equals 1. So that is just equal to a squared omega squared, which gives us an expression now for v squared. So we can say v squared is omega squared a squared minus s squared. So we've got an expression for the velocity, and this is going to be useful now, because if we're going to say, okay, let's look at energy. So our kinetic energy, a half mv squared, and of course our velocity, we've drawn here that velocity is a function of time. We also know that displacement is a function of time. So we've got velocity is going to be some function of displacement, but we've got two parametric equations here, v and s. But what if we eliminate t and write v as a function of s? This is the sort of thing we do with parametric equations. Well, we've got this here. This is now v as a function of s, and we can plug that into here, and we can say, right, we've got a half m omega squared a squared minus s squared. That is our kinetic energy as a function of displacement. So we can see, these things are all constants at the start here. M is a constant, omega is a constant, at least with the oscillations that we're looking at. A is a constant, it's S that's varying. So we've got kinetic energy just as this function of displacement. It's a negative parabola, a negative quadratic that we've got here. So if we draw out, and because we're looking at energy, we don't have to worry about the negative axis. So let's draw kinetic energy against displacement. Of course, displacement can be positive or negative. It's going to be a maximum when s is 0, because we're just going to get a half omega squared a squared. That's going to be our maximum here. That's a half m omega squared a squared, our maximum kinetic energy. We're going to get a minimum when s squared is equal to a squared. So when s is plus or minus a. So that's our minimum energy here at minus a. We've also got minimum energy over here at a, and we know this is just a parabola. So we're going to draw our parabola going through that, and that is our graph of kinetic energy. Put the label in red as well to match the graph. Kinetic energy against displacement. Now, of course, while these things are oscillating, we've got this continual transformation between kinetic energy into gravitational potential energy, or some form of potential energy, depending on what it is that is changing throughout the course of the oscillation. But if we've got something which is bobbing up and down, then we've got some kind of change going on in potential energy. This could be potential energy in the spring, but we've also, of course, got potential energy of the GPE change in the object as well. But we've got some kind of potential energy change, because if it isn't, actually I'll change this to blue. so it looks different. If it isn't kinetic energy, of course, it's going to potential energy. What's happening with a pendulum swinging backwards and forwards? There we've got GPE changes if the pendulum isn't extending in any way. So the type of potential energy or classification of potential energy may change, but we've got this continual transformation between kinetic energy and potential energy. And this has always got to add up to the same amount. We've got to have the same maximum here because we've got conservation of energy. And these graphs are going to be opposites of each other. We must have 0 here if we've got maximum kinetic energy. And then we've got maximums up here in order to keep constant. These two graphs, when I draw them in, have got to add up to the dotted line at the top. So we've got the parabola going the other way up. We've got the positive parabola in order to make the total of these two graphs equal to this fixed amount of energy that's in the system. So that's looking all good. We could also see then that the kinetic energy is going to be, because it's proportional to v squared, is going to be proportional to sine squared on this. So if you were going to draw out the energy versus time rather than looking at energy versus displacement here, I shouldn't have drawn the negative part on that because we're still looking at energy, so there's no need to have negative. So let's go for let's come back to the kinetic energy versus time. This is proportional to sine squared, so we're going to have, let's start it at 0 if it's going with sine squared. I won't bother with an initial phase shift. Let's just try and make this as simple as possible. So we're going to have kinetic energy doing this because it's going to be something to do with sine squared, and then our potential energy is going to be the opposite. It's going to be to do with cos squared. So we're going to be flipping in the gaps like that. Again, they're all going to be adding up to the same amount everywhere that we are, in the same way as we've got these graphs here. So that's our kinetic energy and potential energy as a function of time. So all of these graphs are fairly easy to draw out. And of course, I suppose, just to never forget the other one that we've got, because sometimes they slip these things into questions where they want you to be able to spot that something's going to be moving with simple harmonic motion. And remember what we add on that our so simple harmonic, we've got our acceleration is proportional to the displacement, and it's in the direction towards the equilibrium point, so it's in the opposite direction. Remember we've got a minus that appears in that, so that is our force is proportional to the negative of the displacement. So whenever we've got a force extension graph where it's going like this, or force extension, force displacement, whatever way you're looking at it, a straight line through the origin with a negative gradient, when you're looking at force as a function of distance, then we want to look at that and immediately think simple harmonic motion. So these are all of the graphs that you should have kicking around in your mind, and be quite happy manipulating when you're thinking about SHM.